Yo, long time no see. It's been a couple of days, you guys. Holy cow. What's going on? What a dog doing? All right. Hello, everybody. Hope you're having a good day today so far. Let's get everybody in. Let people roll up in here. Cool. Correct. Come on, where's the push notification? There we go. Okay, nice. All right, we good. What's up, everybody? Welcome back in to the stream today. It's been a little bit. It's been a few days. Sorry if you guys missed me and I lost a bunch of friends over the break there. We're back here. We're going to be teaching ourselves some computer science and programming here today. Or going to be rather just programming. Let's go ahead and get into this today. I'm excited for today. Let's look up a couple of songs here we want to play today. Um, cool. All right. Cool. Welcome in, everybody. Hope we're having a good day. Let's go ahead and get some coding going today. So today's gonna be fun. Let's go ahead and open up the Discord real quick. Let people know what we're doing. I am live coding. Okay. I'm hyped. Okay, cool. All right, let's get into today. So, welcome everybody. Today's actually going to be a fun one because we're going to be doing something biology related. So, actually going to use the old degree here and going to bust this out. Have you guys ever heard of a little thing called polymerase chain reaction, also known as PCR? So polymerase chain reaction is a way that we can duplicate a segment of DNA over and over and over again, so we can actually amplify it to a point where we can, detect it without having to, sequence the whole genome, like the whole genome, which is fairly expensive, whereas PCR is fairly cheap. It's a very low-level, basic definition of PCR, but we're going to go ahead and get into this. I wanted to try to see if we could create and write a kind of simulator to do this as you would in the lab. Similar to what we did in the past. It's kind of going to be like one of those like MIT problems that we've been doing in that course that we haven't finished. Oh my gosh. We would fail school again if we went back. Just because we would not finish classes. We'd get to like the last week and then last couple weeks and then stop going. With this track record we're on here. All right, so today is going to be kind of fun, I think. I have some ideas of what I already want to do. I kind of wrote in my notebook some basic objects I wanted to structure out here in Python and see if we could build this sort of simulation. Now you're gonna have to bear with me as I've been used to writing some code in C for the past couple of weeks. So we're switching back over to Python here. So mentally I might be a little slow trying to syntax Python here. Okay, or lack thereof because there is none. Okay. So what we're gonna do first is we're gonna Python -m v. I'm going to call this dot, or let's call it v. Okay. Let's go. I think if I actually clear this terminal, it might auto detect my v. Yes, it does. Nice. Let's go. Touch. Get ignore. Or dot get ignore, right? Okay, let's code dot. Okay, so in here we're gonna put v, so I'll put environment variables. And we'll also put like PyCache variables. Is it like this? Is it slash PyCaches? I think so. Okay, I'm not sure. I'll have to come back to this. We'll see. I'll look it up here. Let's look it up, whatever. Get ignore PyCache. Oh, it is slash. It's PyCache slash. Really? Is that same thing for VNV? Oh yeah, it's after here. My bad. Okay, let's go. Let me go to my GitHub here. Own Path, how's it going? Welcome in. Welcome back. Let's go to here. repositories. One follower away on GitHub from 150. Hit it with a follow if you want to be that 150. Pi PCR. Okay, cool. So now if we go, I already did. Oh, I just added readme. Okay. All right, we're set up here. Cool. Let's go ahead and get into this. Hey, AJ, welcome. Shrouded Data, change username from YouTube. What's going on, dude? Welcome back. Oh, I did start Twitch. Okay, good. All right, let's go ahead and get into this here. So I'm going to call this objects. Okay, and then we're going to have, obviously, a main.py here. In my objects, I'm going to create a file for, we'll call this, where's my notes? What did I call it? I called it, so we have thermocycler.py, and then we have a, what the heck was my second object I called it? Hold on. Oh, that's right. It's just the simulator. PCRSim.py. Okay. Let's see what we can do here. So, the idea here is we're going to simulate PCR, which is a lab technique used to duplicate and magnify genetic sequences by up to 1 trillion copies within a short period of time for very cheap. It consists of a few different constituents that you need in order to do it, along with a heating and cooling process in order to cause the chain reaction to happen. Just in long story short, so we don't have to get too into the weeds here, it is that you have a solution or a buffer solution that you have some DNA in there that you would like to copy. In order for us to know what sequence we want to copy, we have to give a starting place with primers, which the polymerase, DNA polymerase, which is used in cell duplication, which we are mimicking here, will attach to the primers and begin sequencing DNA by pulling in what you need to sequence DNA or to duplicate, single-stranded DNA into double-stranded. Is nucleotides, right? You need those nucleotide building blocks, those proteins, in order to actually, pair them up and make this double-stranded DNA. So you have to also have those in the solution, of the buffer solution as well. And primers, nucleotides, DNA, buffer. Primers, DNA, buffer, nucleotides, and polymerase. Okay, I think that might be it. Maybe there might be one more thing I'm missing, but that's kind of the gist of it. So in the case of lab, like synthesized DNA duplication here, is we use a heating and cooling process, like I said, using a thermocycler. And these thermocyclers, heat to specific temperatures and maintain those temperatures for certain periods of time per its programming and whatnot, and decrease and while also mixing and causing reactions to happen at certain periods. Now, what happens is that when you raise the temperature up to, I believe, about 90 Celsius, if I look back at my notes, the double-stranded DNA will begin to separate. Then we can lower the temperature down slightly to maybe like 75 C. And there, the primers will begin to bind to the positions on the single strands that are, the pairs that it'll bind to, or kind of like line up to, yeah. Then we have, and then I can't remember if we lower the temperature even more from there to cause the, or maybe we raise it one more time to make that. No, maybe we lower. I can't remember. Lower it or something like that to cause the transcription to happen. Yeah. So it's a pretty simple process overall, but it's a really cool technique. Not too much to it. There is a process of qPCR, which is real-time PCR, which quantitative PCR, which is like used at certain periods in between the sequences to run gel electrophoresis and use fluorescence to detect quantitative data points of these DNA in between those sequences and stuff like that. So let's think of how we want to get this started. So we have a PCR simulator, which is going to be a class. So class PCR sim. And then what we're going to have is an init. Ah, my gosh. And we're going to have self here. Within the PCR sim, to create this sim, you're going to have a... So we want to keep things specific to the thermocycler. So maybe I'll also work on the thermocycler here as well. Oh, not mine. Okay, and so the self is going to have a, that's kind of it for what you give it. So you're going to have a self dot temperature, temp, is equal to, we're going to do import random, and we're going to do random dot random. This gives you a random random dot random. Rand int. Return random integer between a, including both endpoints. Okay, cool. But this is random integer. I only want a random integer, range. What does rand range give? Choose a random item from range stop. Choice. from a range object. Let me see. Does random.random just give you a float between 0 and 1? I can never remember. Yeah, floating point number between 0 and 1. Okay, I gotta think here. I forgot how to use this cheese. Okay, yeah. So we'll do rand int between, let's do 23C and 25C, 26C plus this. Okay, so we'll do that, which will give us a random float value with a decimal at the end. Between 0 and 1 inclusive. Hopefully that works. Is there a better way to do that? Random float in a range, Python. Random uniformized generator random float within a specific range. Oh, random uniform. Alright, cool. We don't need to do that. Okay. So that gives us temperature. Self dot cycle equals 0. Self dot current cycle is equal to 0. So if cycles, current cycle, we're gonna have temperature. Okay, so then okay, cool. I think that's fine. So temperature. Okay, so we're gonna have on the thermocycler, we're gonna have a couple of instance methods called def heat up given self, and we're gonna say desired temperature. So heat up to desired temperature, which is going to be a float. And then what we'll say is if the desired temperature is less than or equal to the self dot temperature, we're going to raise a value error saying heat up error, heat up failed. Heat up failed. Thermocycler is already at and then we're going to do self. I guess we'll just put in the desired temperature here to make it kind of self-explanatory. Okay, and that's fine. So the desired temperature can be less than or equal to temperature, can't be less than or equal to temperature if we put this in. So else what we're going to do is I want to look up on Wikipedia. Let's look up a heat ramp function. Let's do thermodynamic heat. Thermodynamic ramp. Let's see if there's like something for like a ramp up to like temperature thing. Any physics majors in here? I don't want to go to the orb, but I might just ask it for a let's just say, is there a math function for well, we want to do, actually let's think here. We might not need to do this. Let's open up Desmos. Let's see if we can grind this out. We want an exponential function, but it's turned on into a side, so is that a log function? Yeah, log of x. Okay, so, and if we give log of x and x is equal to 10, how do I plug in a value for the variable? What if I say this? This just... So how do I skew this? It's been a while, guys. That's how you raise the asymptote. Right. Okay. Okay, so let's maybe see here. Let's go log x for a heat ramp function that canonical heat ramp function best choice. Exponential approach to a maximum. A temperature target less than temperature target less than temperature start times e to the power of k times t, which is ideal. Asymptotic approach is t the target. Smooth, continuous slope parameter k check directly controls ramp speed. If you really want a log-like expression, you can normalize the log function to cap at a max. Okay, so in this instance, what is k and what is t? T is time measured in whatever unit you're simulating using a second. T equals 2, 0. Okay, so this is what we'll do. So the thing is I need to figure out how like a time component of this is gonna work, right? So I have a heat up. So in my PCR sim, right, I'm gonna have a self dot um, like ticks, right? Like these are gonna be the total ticks of the simulation, right? And then we're gonna have like a self dot tick rate. Is it just ticks like this? Tick rate, which is equal to, let's just say 1, right? So for every loop cycle, you get a tick. But how do we control how fast the loop cycles move, right? This is where I'm so who here is a game developer that knows how to do like time cycles for like clocks, like game clocks. So if I was going to have an over, think of it like this. I'm a person, so I'm running this PCR sim. Now, I kind of want to make it to where I think of it as if I put myself in 2x speed and I moved it really fast and the world just moved at 2 times speed, right? So if I had ticks at 0 and tick rate at 1, um, right, that would what causes the, let me think here. Let me turn on my music. So we know a while loop will just continually move after all the actions inside of it are performed, all the statements, right? Now, if you take a time at the beginning of your loop and a time at the end of your loop, or at the time at the beginning of the statement and the time at the end of the statements, and make sure that that time, and then you could just wait or sleep, whatever, for the remaining time within the, according to the tick rate, right? Or something like that. But the thing is what happens if a process takes more than one like second? So let's just think about it like, yeah, okay, so get delta, see if it's more than some portion. Oh God. Okay, so before I get into this, let's talk about a game loop for this overall sim. I PCR sim is my object that will control time. It will send signals. I don't need to give all that information. I am trying to learn how to control time on like, this is kind of confusing to like describe, like control time for both when functions take less than a full tick or extend beyond. I am also confused on the general idea of ticks and like tick rate and how I can use this to speed up my sim, like a like my chemical, like a Sims game on 2x speed. Okay, let's get some feedback. That's exactly the right moment to talk about this. If you get the time right, everything else in your sim becomes simpler and more realistic. If you get it wrong, you end up fighting your own loop forever. I'm going to be very explicit and conceptual here, no code. Let's think game engine, not WoW loop that sleeps. Perfect. No code, exactly what we want. First, what a tick actually is, the clear confusion. A tick is not one unit of real time. A tick is one update step of the simulation. That's it. A tick has no inherent duration. Time only exists because you decide how much simulated time passes per tick. Ah, okay, so I make up the tick, basically. But I feel like you're bound at some by like, okay, hold on. Let's just keep going. Two different times you must keep separate. You must always have two clocks. The real time, the wall clock, how long the CPU time actually takes, irrelevant to the biology, only matters for the pacing, the loop. And two, the simulated time or the biological time, what PCR sim cares about, seconds of PCR heating. Your loop does this conceptually. Every tick advances simulated time by a change in t. Then update the system. So the change in time equals how much simulated time has passed. If the change in time is 1 second, real-time simulation. Your simulation functions do not consume simulated time. They consume CPU time, which is irrelevant to the model. Okay, that's kind of where I'm being confused at. So a function that runs in 0.1 milliseconds and a function that runs in 50 milliseconds both represent the same delta time of simulated biology, if you say so. So a fixed time step loop is what I want. Choose a fixed delta t. Each tick advance the simulated clock by delta t. Update all systems by delta t. So you store time. Store time, target temperature. Confused on, so we have to keep track on two separate times. Long actions are spread across many ticks. We got a lot of stuff here. Okay, then your iteration speed is increased by changing the number of iterations that occur in a single second. So imagine a board game, not a video game. Every turn, players update the board. A turn does not mean, quote, 1 minute. A turn means advance the game state once. That's a tick. A tick is just, okay, everyone update. No clocks yet. Imagine a game board, not a video game. Now every turn, players update the board. A turn does not mean 1 minute. A turn means advance game state once. Okay, now introduce simulated time. You decide each turn represents 1 day. Now, 1 tick equals to 1 simulated day. Later you decide, actually each turn represents 2 days, so 1 tick equals to 2 simulated days. Nothing else changes. Same rules. Your while loop is just take another turn. Each loop iteration equals to 1 tick. Inside PCR sim, you keep a variable. Functions are just math. You are declaring this tick represents a delta t seconds of biology. You chose delta t to equal 1 second. 1 tick equals the simulated time. Oh. You do not run a loop for 30 seconds and block the sim, you wait. And wait. Instead you say heating there. Every tick you compute. Heating started at sim time. Given the current sim time, what should the temperature be? When sim time less start time is greater than or equal to 30 seconds, heating is effectively done. Oh, we go. Okay. So we'll say ticks here. Self.sim time is going to equal to 0 as well. So we have self.ticks is going to count the number of but then we have a self.delta t, which is equal to is our factor, right? For every like a tick of time, so we'll just have delta t equal to 1. So this is 1 second, right? Okay, so I have a simulated time and a self.delta time. Okay, got you. And then I would give it Okay. Trying to think of. Oh, sorry. Listen to some chats. Hey, Tim. I'm not sure what you mean, Jimmy. Okay, so if your loop runs 100 times in 1 real second, how many simulated seconds pass? There's no inherent unit. 100 loops equals whatever amount of simulated time you decide it is. That's not a dodge. You must choose one number. Okay. Okay, I'm trying to think here about. Sorry, I just keep saying that, but I think I'm getting close to figuring this out. Okay, so the speed is 1.0, right? So then if I have a thermocycle, so I have a def okay, so what we're the thermocycler is going to have a run sim. Okay, so what's going to happen when we run PCR? So we have run PCR here. I'm going to. So we want to make a loop that will. Just trying to think of what I want to do. Probably should maybe plan this out a little bit better off stream, but this is what it is. So the heat up function of the thermocycle is going to have a function that's going to return temperature back to it's not going to return temperature back to the PCR simulator. It's going to thermocycler has the temperature variable and within it that it's going to heat up to that temperature. Now if we have a heat ramp function like we talked about earlier, Which translate troubles the ramp. T equals time measuring whatever unit similar to use seconds must come from milliseconds. K is a heat rate constant. Okay, so let's just do this. Let's just start messing with stuff here. We can worry about time, I guess. Maybe. So I'm gonna say start time, or say start equals to 0, just to keep track of something here. We're then going to okay, while self dot temperature is less than or desired temperature. Cool. So while self.temperature is less than the desired temperature, we're going to continually increase the temp. So what I'm going to also add on here is a constant called K, which is how fast we ramp the heat. So I guess we can put this in here as 1 over some value of time, right? Per second. So this is going to be in our exponent, but it's going to be a negative exponent, right? So larger K values will increase the ramp. Smaller K values will cause a gentler ramp. So I guess let's just do a half for now. Interesting though is, could we put in, we start at 1, do 1 and 2. You approach the temperature slower and slower and slower on each different K ramp. If we start the top at 1, do it here, will it get there right away on the first ramp if you have a factor of 1 for this constant? I don't know. Oh no, but it's going to cancel out because it's going to be multiplied against the time. Okay. So I guess we'll just have a constant ramp factor. Well, it is a constant, so it shouldn't change really, right? So we'll have a constant here. And then we'll go ahead and plug this in. So we're going to say, I'm first going to call print to, well, actually, hold on. I'm all over the place, you guys. Bear with me. So we'll say temp of t, or should I say that like a temp for a function? Temp of t for a variable name, or is that stupid? I guess we'll just say new temp, variable name struggle, desired temperature less than our function. Let's have our equation written down over here, is less than the target again, so the desired temperature less than the start temperature. So self dot temperature So I wonder if the start temperature has to stay the same throughout each as we increase the time variable, which is here. So I need to import math dot raise the power of x, which is negative k times we'll say t equals to 1. And then this is multiply. Okay, so, and then if we print new temp here, and then we'll say self dot temperature is equal to new temp. And then we'll go as into main, we'll go import thermo. No, it's from, my bad. Didn't react too much. No. Create a thermocycler. So that's 1 second. So what we're going to do though is this is going to cause the total game time to go up 30 seconds, go up the total amount of t you get for this function, right? So we'll say times 0 at first. Then we say t plus equal by 1. Yeah. Okay. Oh, we're better now? Stream's good now? My fault. Think we're okay? Okay. So t will plus equal by 1 there to continue the ramp. So let's run our main function here. So we'll go, so our thermocycler will get a temperature which is random, which is a starting temperature between room temperature. And then we'll begin to ramp up until self.temperature is at the desired temperature. So we're going to call test dot heat up, and we're going to heat up to 75 C. And then I guess we'll run this. Yeah, see, it ramped up and then it got there. Boom. Okay, nice. Okay, so then let's just round this off to 2 decimals then. Why did it like print all at once? Why did it not print? Oh, I think it's just really fast. Oh, okay. If I call a is sleep in the, no, is it in sys.sleep? Is it system or is it operating system? Or is it OS? OF, bruh. I forgot. Oh, it's time.sleep. Trolling. None of those. Bro. Alright, I want to see if that'll kind of do it. Okay, yeah, okay. It is just going really fast. I didn't want to make sure it wasn't like something was wrong. Okie doke. That's fine. So that heats up the and so the amount of time that elapsed was the amount of cycles. So if at the end of this loop I print and say time elapsed, or say heat up time, and we say into here, ooh, I like this song. 74 seconds. Okay, so it took 74 seconds to heat up. That's crazy. So that heat ramp factor is way too unrealistic. So let's make this like 1/5. 184 seconds. Almost there. Let's actually round this off again. We forgot to do that. 2 digits. I guess we're on to 1 digit. Okay, yeah. And then what we'll do is, does this give it, we'll just make it like this. Okay. Alright, that took 36 seconds with that ramp factor. We went from 25 to 34. We're looking for more like maybe every 2, 3. So let's go bring that up. 57 seconds. In 1 second, it heated up 6 degrees. This thing's on fire. That is not gonna happen. This has got to be probably quite large, or quite small, I mean, but large in the denominator. I feel like that's still too. What if I make this like drastic? 1/25. Well, maybe this thing gets hot fast, man. Maybe it gets hot quick, and then it takes a little bit more energy to get up to that last little level or fine tune it, which does kind of happen realistically in the lab sometimes. Interesting. Okay, cool. So let me actually, what do we think about that ramp time? What if I made this like 1/50, like a really low ramp time? So let's do a little math here. 5 minutes to heat up. That's pretty long. So I'm going to say if less than or equal to desired temperature, I'm going to give this a factor. We'll add in a temperature allowance, which will be 0.2. Less than the temperature allowance. Right, so what that'll do is just make it so that that ramp is allowed on that final one. And then what we'll have to do is, because we're allowing for take this off, go here, we'll print out here, we'll do this here, print out self dot temperature, and then we'll say at we'll insert self dot temperature here, close these quotes, increase that, and then at the very end we'll take this as well and print out the current temperature. Actually, what I'll do is do heat up complete. Equals to heat up time. Okay, so what that'll do is dash. Let me actually move this over here and this over here. So what that'll do if we run this, so now we have this. Oh, so yeah, it doesn't run one more time. Do we need to increase the temperature to the allowance, basically by the allowance at the very end? I want to do 4 minutes though. We need to lower this down. Let's do 1/15. Okay, a minute and a half. It's not bad. Okay, because it doesn't do the final iteration, and it's because it's within tolerance, it doesn't loop one more time and go up to the spec, which is interesting. So I just need to increase the temperature by the tolerance, or by the allowance at the end of the loop, which, I don't know, is that kind of hacky? Right, that'll raise it up to the desired mark, kind of saying, oh, it got up to that final tick or whatever, that final, right? I don't know. Hey, Slow, how's it going? Okay, so that's our heat up function. It's pretty simple. Nothing too crazy. So we just have a desired temperature. If the desired temperature is less than or equal to the current temperature of the thermocycler, then and we have an allowance here of where we're allowed to kind of wrap up, kind of assume. Or like a tolerance, basically. So if now what I could do maybe to make this even more variable is apply like a randomized factor, like maybe between 90 and 95%, or 90 and 99%, or like 90 and 100%, to kind of reduce it down by a certain kind of randomized factor, either by certain between 10%, in order to kind of mimic just like any abnormal, entropy effects from the environment or whatever. But that's kind of like maybe beside the point. Whatever. Okay. Anywho, I think we are good to go. All right, nice. That is our heat up function. So for our def cool, we have a cool down function, which is going to be fairly similar, I think. Right. And so what this one's going to do, we just flip the sign. Oh, got you. So let's just do this. Let's just do change temperature. We're going to do if desired temperature is less than, if it's equal to self-dot temperature, then thermocycle is already at the desired temperature. If the desired temperature, or so we'll say, shoot, say if desired temperature is less than self.temperature, meaning that we're going to heat up, right? We're going to do this out front. We're going to take this. Put that there. Bring those in. Okay, so what's going to happen here is we have new temperature, which is going to be getting, if desired temperature is less than the self-dot temperature, we're going to do this. We're going to heat up, right? Well, if I actually, I don't even think I need to do this. I think I just take this back. Take this out front here. If while do this, take this, exit here, here, copy down, else so if the desired temperature is less than the start temperature, that means we're going to heat up. So we're going to print that we did heat up. Else we're going to print cool down complete. Cool down. Now I wonder what if I can just do this, maybe print this back. We'll do a flag out front. Elif. So I'm changing a lot of stuff, but I think I'm doing it this the right way. So if elif if it's less than, then we're going to do heat up. If it's equal, so here we're going to set so if the desired temperature is less than the start temp, we'll put the change type to heat up. We'll do this math once. We'll print once at the end for the change type change type. So by default, we can set it to cool down. So if the change type is cool down by default, we'll ask the question if it's less, if the desired temperature. Oh, sorry. If the desired temperature is greater than the start temperature, right, then change type equals to heat up, meaning that we're going to increase the temperature. Else, if the desired temperature is equal to start temperature, then we're going to raise this error. Now we probably just ask that right off the jump, right, to raise the error right off the bat. But I don't know. Okay, I don't know. We'll see. What do you guys think? Should we raise the error at the start and not even establish variables? Okay, so else we can just leave the change type as it is and cool down, do our while loop, print current temperature, and use the change type. Now we just have one function here. So if we go to our main and do change temperature to 75, heat up complete. Oh, so ooh, right. I'll just say change temperature failed. Thermocycle is already at desired temperature. Okay, and so then if we run this for a lesser value, let's say 10, then what the random will be dang, failed. Well, self-dot temperature is less than. Ooh, shoot. Oh, that's not going to work. Crap. Right, because while the temperature is less than the desired temperature, well, it is, so it's not going to run. So I guess we'll say, we'll ask this in a conditional at the end. We kind of need like a do while, right? But so we'll say, we'll take this. Get away, type in. Stop that. Oh my god. Dude, get out of here. Why is it doing that? Okay, we'll take this. While true. We'll say if oh dang. Should I just have left it? I just do this for nothing? We're gonna do this. If the self-dot temperature. don't want to redo it again. Whatever. How could I maybe modify this? Let's think maybe. How could I modify this conditional? I would have to check if it's cool down or heat up for the change type. Right. Hello everybody, welcome into the... Okay, so let's just do this. If it's... Well, I want to actually see if this is possible. I'm gonna get some feedback. I'm trying to accomplish both, but the logic is preventing. This is supposed to be outside of the loop. Huh. So we got this. Okay, let's just whatever. Screw it, dude. This is stupid. Wow, so the temperature less than that. I mean, we're gonna have to like, I don't really know. I didn't really want to duplicate code here. Maybe there's a better way of doing it, but I thought I could maybe combine them. Plus. There you go. Start off at 24.9 and we drop all the way to 10. Temperature cool down. Boom. Okay, cool. That does that. I like that. That looks good. The only thing I don't like is that we're kind of using a lot of code here, which I was kind of using these change types. Don't need that then. Okay, cool. This should be working then for both. Yes. All right, this function is dynamic. So I'm gonna take this, I'm gonna say, I split the logic, but I tried originally to not dupe code, but here I am doing it. Okay, so let's take this, put this here. Okay, so there was a way to do it. Let's learn here. So it did what I wanted. It did what I should have said I should have done earlier, which is put the error raise at the start. We set change type after this because we don't need to set change type if it errors. Equal to heat up if desired temperature is greater than the start temperature, else cool down. So then what we're going to do is we're going to while true. We're going to compute this. Get rid of this, put this here. So if that temperature equals to that. Oh, so bidirectionally aware here. Oh, interesting. That's what I was missing. So if the absolute value of self.temperature less than the desired temperature is less than or equal to the temperature allowance, right, then we're going to break. Right? So if you take the difference between the two, whether positive or negative, and that is within the less than or equal to the temperature allowance you break, you could just use the absolute value. That was easy. Come on, Mike. Then you advance simulated time. But then, to handle the case where we need to appear the number at the target, right, we have to set self dot temperature equal to the desired temperature. And so that should still work. Cool. Nice. So then let's round off that minutes. Nice. Let's do to 2. Okay, that's nice. Okay, so now we have a solid change temperature function, which looks really, really good. Works for both up and down, and will increase the time. So what this is going to do is going to return going to return T, right? So it's going to return the amount of time it took to change the temperature. So then in my PCR sim, if I run the simulator, let's say this simulator we're going to from objects dot thermocycler import thermocycler. We're going to say thermocycler is equal to the or I guess I'll say self dot thermocycler is equal to a thermocycler object, right? And then what I'll do, now we have this attached to this PCR sim and self. This is VS Code in Mac. Welcome in, Peterson. Appreciate you being here. Okay, so we have run PCR. We'll run the PCR for self. So what it's going to do is something similar to this. Let's say that all we want to do is increase the temperature in this run PCR to 100 degrees. So step 1, right, this is going to be, let's just say self.thermocycler dot change temperature to 100, right? So now all we need to do actually is call from objects dot PCR sim import PCR sim, and then call a simulator is equal to PCR sim, and then what we'll call is sim dot run PCR, and that's it. And now if we run this, we get our temperature increase up, right? So pretty cool. Okay, so that's now what we can do is just add on functions into this method for PCR sim for doing, various things. Kind of like stages, right? We've got it kind of all set up now in objects. That's kind of why it's fun. It's kind of difficult at first, but it's definitely worthwhile to kind of plan out these objects and how they're going to interact ahead of time. Now, I didn't do the best job. I did do some thinking live here on stream, but I did take about an hour yesterday or 30 minutes while I was watching a show with my lady to kind of think over this and take some notes in my notebook about what objects I wanted, what some methods were, and how they were going to interact. And I just wanted to figure out the time aspect here on stream. So now it is making more sense. Whereas we have a delta time, which is basically our factor, which is per second, which is 1 second per second. We can make it 0.5 seconds per second or 2 seconds per second, right, to speed it up or whatnot. Um, and this delta t will be so let me ask here. If my PCR sim has delta t, does this need to be fed into the thermocycler.change temp as the t variable? That'd be sim time. Wait, no. It should not do that now. My thermocycler change temp is returning the t, which is seconds elapsed No, I don't. So, okay, so I run the thing which creates a sim time as 0. It does this and returns the amount of time back. So this gives you back a time. So I have this. So block and call doesn't run on internal level. Oh, that's stupid. Okay, so I'm actually going to remove delta t and then go self dot sim time plus equals here. And so this will do the total amount of time it took to do this simulation. So what we're gonna do is there's a list of temperatures, and these are gonna be, let's look up NDC. So 194F. Okay, so hold on. Where's my notebook? Where is my notebook? Okay, where is my notes from yesterday? Okay. So denaturing is 95C, which is Okay, so denature. The first step of the regular heat cycle event is with heating reaction chamber to 205 C for 20 to 30 seconds. Okay, so I'm going to make a function here called def. This is going to be called denaturation. So I'm taking self, and we're going to do this. And we're going to go temp temperature is equal to 205. And then what I'm going to do is go like this. We're going to call this. Where's my music? Okay. All right, so what we're going to do is then go up to the temperature, right? And so this is going to be, right, increase temp to 205 C, 205 Fahrenheit. We're going to hold temp, hold at 4 seconds. Okay, so we're going to add in a method to our thermocycler here. So this thermocycler is going to have a method here, which is going to be def hold temperature given self, and right, right, so, and then we're going to give it a time, hold time, which is a float. So we're going to say t equals to 0 while t is less than hold time. Right, while t is less than hold time, we're going to print and say this temperature so something like this. Okay, temperature so we'll say print f, what was it, print hold period started, hold period start, I'll print this, hold, say temperature hold complete, temperature equals to blank held hold period equals to t seconds or minutes. Okay, so t equals to 0, t plus equaled by 1, temperature equals to this, hold, current, hold. Temperature hold. Five. Temperature hold complete. Temperature equals to this. Okay. So we hold period start, or so we'll say temperature hold at hold time, or sorry. Okay, temperature hold at this for blank start. Started. While t is less than the hold time. So while t is less than the hold time temperature of 5, right? Temperature hold status. Okay, cool. Now let's see what happens here. If we go, we're gonna go, and then we're gonna return t. Can't forget that. So if we go self.simTime plus equals to self.thermocycler.hold temperature for random dot random int between A and B, which will be according to my notes here, (20 to 30 seconds). Okay. So now if we run this PCR, run PCA, we're going to do stuff that. Comment these out until we're ready for them. Now if we run this. Oh, wow, loop, what the heck? Okay, so cool, we start. Heat up complete, temperature equals to 205. Heat up time 99 seconds. Temperature hold at 205 for 24 seconds started. Let's go back to my thermocycler. You kind of add in some descriptions here. Okay, so then so let me go really quickly here to, not here, but here. Is that Fahrenheit? Fahrenheit, Fahrenheit, Fahrenheit. Okay, so now if I go main, run. Okay, so current temperature is 0 seconds, 23.7 Fahrenheit. We increase, right? Heat up time complete, temperature equals 205. Heat up time equals to 99 seconds. We held temperature hold for 229 seconds started. Temperature equals to 205 Fahrenheit. Temperature hold status. Right, we'll do these temperature holds. So we want to do we want to include the last second. Okay, so hold temperature. Temperature hold complete. What do I want to change? Okay, so the of okay, cool. So the status now works good. Let me get a little bit of feedback on this hold temperature function. Should be pretty straightforward. cool. So then what we're gonna do is in our PCR simulator, we're gonna do this. Okay, PCR sim started the denaturation period. Current temperature. Heat up complete. Temperature is 205. Heat up time. Hold period. Holding at 205 for 30 seconds. Or about 30 seconds. Right? Nice. Okay, so then what we can do is really quickly, I'll write up a def self dot annealing function, right? So this one is going to be somewhat similar to this, but we have annealing period. Desired temperature is going to be 50 to 65. So we're going to do random.rand dot uniform 50 to 65. 122 to 149. We're going to set temperature to 130 Fahrenheit. Fahrenheit. Decrease temp. Hold temp for 20 to 40 seconds, so another 30 seconds. Okay. So then what I might do is go to thermocycler. Let's print here. Okay, so annealing. The two different primers are typically included in the mixture. One for each. Yeah, so that's the annihilation period. And then we're going to have extension. Right? So the extension is going to be something similar here. Right? For the extension period, we're going to be between 72C, 167 and 176. Right? So at the end of this one, I'm going to say primer. Annealing period complete. Primers. Say DNA primers. Bound successful. Also, it's annihilation period complete. Copy this. Okay. So then you PCR extension. Okay, so the time common is 1 minute per 1,000 base pairs for Taq polymerase. So the common is 1 minute per every 1,000 base pairs. So what we're going to do is extension. You have to give base pairs, which is an int. Okay, right. Which will default to a 1,000 base pairs. Okay, so the extension period is this. So the base pair is 1 minute per 1,000 base pairs. So minutes, so 1 minute per every 1,000 base pairs. So time equals to 60 times the base pairs, right? And so this will be the extension period. You have a temperature of Yep, Lake's falling asleep. 167 to 176. We hold for 30 seconds. Oh, my foot's falling asleep. Oh, my foot is falling asleep. Come on, wake up, wake up, wake up, foot. Okay, you're okay. Okay, and then, so that's going to be a hold period of time. Right. Nice. So then if I get rid of this and run the main program, boom. $60 seconds. For every 1 minute for every 1,000 base pairs, which is 60 seconds a minute for every 1,000 base pairs. So the 1,000 base pairs, when I clone, 1 minute for every 1,000. So this would take 1 minute. This would take 60 seconds. Yeah. Okay, that's better. Here we go. So okay, started. Denaturation period started. Heating up. Heating up. Heat up complete. Temperature is 205 Fahrenheit. Heat up time is 99 seconds total. We're going to temperature hold at 205 for 35 seconds started. Held for 35 seconds completed. Temperature 205. Hold period of 35 seconds. Denaturation complete. We have the annealing period. So current temperature, we're going down now. Cool down complete. Temperature is 141. hold status function. Okay. This is a good place to stop off. Current temperature is decreasing. Cool. Alright, let's add this up. Cool. All right, you guys, that was successful. We got pretty far there, a lot further than I thought. And all we need to do now is just loop over a number of times until we hit 1 trillion total sequences met within an instance variable, and it's done. It'll basically double each time, which will be cool. So we can say self.sequences equals to 0. Goes to 1, right? Are you learning to program for fun? Yeah, basically. I work as a chemist, and I don't really have to program at all as a chemist. At least in my current job. So then what we'll do, or not sequence system. So PCR sim is going to have self sequence. Okay, that sequence is 1. Then we're going to say while sequences self dot sequences is less than. So this is it's million. Mm. $100 million. Billion. So we're going to make 1 trillion copies, right, which is going to be 9 zeros and a 1. No, that's a million. That's a billion. Oh, whatever. We'll say so while cycles so 1. So we double every single time. So we're going to print F here. PCR sim. Cycles. Okay, so the PCR sim complete cycles is this, elapsed time is this, and then we'll say print here one more time for so if we run, there it goes. Hey Mahan, how's it going, dude? Yeah, I cut my hair. Let's see what happens here. Come on. Come on. It's tweaking. Am I infinite looping here? Oh, yeah, I am. My bad. There we go. Like, why is this going on so long? Should not be going on for that long. Finished like that. Bro, okay. Oh, look at that, guys. We did it. We did it right. Look at that. Look at that. We did it right. For 30 cycles. Boom! Let's go! We just simulated PCR successfully using Python. Woo! All right, you guys, thanks so much for joining me here. If you guys missed this session, make sure you guys go back and watch this one. I know I was a little bit quiet during the middle as I was kind of working through some bugs and kind of figuring out how I wanted to structure the objects and whatnot, but this was a really good stream, in my opinion, if you're learning Python to kind of study from to see, okay, what does some basic object-oriented structure look like? How can we get some of these objects to interact, and writing some basic loops and whatnot to actually, simulate some sort of real-world example. So this is kind of like a real kind of Python project that you might make to do some sort of, simulations for data analysis or whatnot. It's pretty cool. So yeah, this is awesome. So, right, we successfully simulated PCR, which is polymerase chain reaction, which is a way to amplify or duplicate a specific sequence of DNA up to like 1 trillion times. so we can get better amplification and read and detection for that specific gene sequence um, in a patient, rather than having to sequence their entire genome, which is pretty expensive, and where PCR is really, really cheap. So that's what the actual benefits of PCR is the price, where you can target specific sequences for relatively cheap without having to do the entire genome. Um, and it's relatively fast. Rather than having to do the entire genome or whatever, you can do the PCR in just under about 30 minutes, or like 181 minutes is how it took about an hour and a half here to complete. Um, it took a 181 minutes, or about an hour and a half. No, not hour and a half. 90 minutes is an hour and a half. It took about 2 hours to complete 30 cycles of this process, which equated to this many DNA sequences duplicated, which was pretty cool. Given certain hold periods and stuff randomized each time, give or take. And yeah, we went over the couple of processes today for actually doing PCR and implementing that into code here, such as denaturization, annealing, and extension, which are all part of kind of changing various temperatures, and then holding those temperatures at certain points in time to allow for certain enzymes and proteins to bind onto the overall DNA, the split DNA sequence into a single strand of DNA. The primers will bind during the denaturization period. Denaturation period. The temperature increases to split the DNA strands apart. The annealing period lowers the temperature to allow for the primers within the buffer solution to attach to the starting places within the DNA sequence that we like to copy. And the extension process allows for the Taq polymerase, which is the heat kind of insensitive polymerase, to be able to actually transcribe and extend this DNA into double stranded DNA by taking in exterior nucleotides. So pretty cool that we were able to do this simulation. Let's go ahead and throw this final output into get some feedback on it. Boom. What your print tells me, if your counting time is internally consistent or maybe over 30 cycles, makes sense. PCR style ramps plus holds. Your control flow is working end to end. Exponential model didn't stall or explode. You sequence counted double cleanly each cycle 2 to the power of 30, which equals to that. It's not a toy loop anymore. That's coherent simulator. Took about 6 minutes per cycle, which is 180 minutes. Final sequence count matches theoretical PCR amplification. This is exactly how sim style time control works. Nice. I am a biologist by trade, or whatever, professional biologist. I have a degree in human biology and a minor in chemistry, and I work as a professional chemist, though. So I use a lot of the same things, a lot of human source materials and mammalian source materials, animal source materials, combining into various products and solutions to build things for hospitals and stuff. Nice. So let me go ahead and we'll push that up. Finished. PCR sim. Multi cycles. Cool. That's really awesome. All right, guys. Thanks so much for being here and hanging out with me tonight. This was a really cool stream that we were able to do. Yeah, so thank you guys so much for joining me. I'll see you guys tomorrow, where I'll be back, continue on with our studies, probably into C. We'll probably keep going in C programming, a modern approach. And I know we want to continue on in our C project that we're doing, which is our custom ASCII kind of timer art that we're doing in C. So thank you guys so much for being here. Make sure you guys join me back tomorrow for that, and I'll see you guys tomorrow. Peace out, guys. Peace out, guys. Peace out.